Good morning, everyone. We have the pleasure of listening this morning to Yang-Hui, fellow from the London Institute of Mathematical Science, professor at City University and tutor at Merton College, Oxford, who will be telling us about some modern geometry and through a playful introduction. We're very happy to be again here at the London Institute for Mathematical Science, who's very generously hosting us for this set of lectures. And please, the floor is yours. Sorry.
Thank you very much. Well, thank you for being here. For those who haven't been in this room, this is Michael Faraday's Apollo room. So we here at the London Institute of Mathematical Sciences are very lucky to have possibly the greatest room in the history of science. So you're part of this great tradition. Thomas is our director over there. So he's hosting, and we'll have Sarah, our development officer. So they've recruited me here so that I don't have to teach undergraduates. So partially. So I'm going to share. So my lectures are going to be was advertised for 2 lectures, but as I was writing them, I realized, you know, it's just not going to happen. It's going to be at least 4 lectures, if that's okay with you. So we're going to find. So basically, what I want to share with you, and I was just talking to Dimitri. I suffered as a graduate student, as we all do. That's the whole point, right? We don't suffer. I'm of the Russian school. All of my Russian friends tell me that I'm of the Russian school of mathematics, which means 1, you suffer. 2, you purify yourself through the suffering. And 3, you're anti-Bourbaki. So let me try to explain what the 3rd means, right? So no, I'm a fan. Look, I have Grothendieck, and I worship every day to Grothendieck. But the point is, mathematics was fun until Bourbaki. Okay, you do not learn mathematics from Bourbaki. The Russian way to approach these problems is to play. You play, you play, you play. Oh, there's a pattern. Let me state a conjecture. Let me state a theorem. Maybe that's the right definition. So what I want to do in this set of lecture notes is to share all of the pains that I've suffered as a graduate student so that you can do this and then go read Bourbaki. Read Grothendieck, because he's the greatest of us all, right? So that's the point of this set of lectures. That's why it's like, you know, cool kid who's like playing. So please interrupt me. I want this to be as interactive as possible. So just a basic outline. I'm going to calculate the number 2 in 4 different ways, the number 0 in 4 different ways, and then make some generalizations. And then through this 4 different ways, I hope you'll get an exposure, because you guys are you know, mostly PhD students, some even like master students, to get an idea of differential geometry, algebraic geometry, and arithmetic geometry, and why 2 appears in so many different ways. And then I'll do a little bit more formalism, and then since this is a theoretical physics crowd, I'm going to make that into how to construct Calabi Yau manifolds, for the sake of Calabi Yau manifolds. And then something that's close to my heart in the 4th lecture, which is I want to convince you the take-home message, or this is very controversial. The entirety of algebraic geometry is an image processing problem for a neural network. That's the point I want to get to. Every single imaginable problem in algebraic geometry is an image processing problem for a neural network. And that's the highlight. So that's me being a fanatic. But first 3 lectures will be uncontroversial, standard stuff. 4th lecture, I may just go nuts. But so far it's okay. So let me start with the number 2. And I'm going to put a date on this. Let's start. See, I'm being very cheeky. I'm not using the blackboard, but since here at the London Institute, we use Hagoromo chalk on real blackboard. But I thought, you know, for a big one, my handwriting is pretty messy. I'm going to at least pretend that my presentation is on a blackboard. I will use some blackboard later, but anyway. So let's start with a convex polytope. Okay? Don't worry about the definition, because the definition is here, which is completely unreadable. I will give you the definition. That's the whole point of doing Russian mathematics. You don't care about this. Only Bourbaki will start with this definition, and then you are lost. Right? Let me just start with convex polytope. That's it. That's my definition of a convex polytope. Okay, fine. You know a convex polygon. Right, a convex body. I'm going to give the definition in a minute. So let me consider a convex polytope in 3 dimensions. otherwise known as a convex polyhedron, many faces. So you can think about cubes. It's convex, so you don't have indentations. Okay. So take my favorite one, the pyramid. So this is the tetrahedron, the four-sided figure. Euler, sometime around 1736, made this remarkable observation. If you take the number of vertices, it's 4, minus the number of edges, which is 6, plus the number of faces, you get 2. Okay. I've been trying to teach my 4-year-old this. Right? This is, you can do that, it's not a problem, right? It's the understanding why 2 comes out. That's really important, right? That's fine. Take the cube. You've got 8 vertices, 12 edges, and 6 faces. You also get 2. Okay. Now, what Euler observed is that you take any convex polyhedron in 3 dimensions, this alternating sum will always give you 2. The proof is very easy. It's proved by induction. You take away an edge, you remove a face, and you remove 2 vertices. Just do this induction, then you can see this is true. So why do I put the date 1736? What happened in 1736? So, yes, who said that? Excellent. Thank you, Jeremy. So the supposedly Euler solved the bridge of Königsberg problem in 1736. So you know the bridge of Königsberg. So I don't know. There are 7 bridges in the city of Königsberg, which is now in Russia, I think. Yeah. What's it called now? What's the name of Königsberg now? Kaliningrad. Okay. So can you go through the bridges just once? So Euler invented topology in order to answer this problem. So he solved this problem in 1736, and that idea is what gave Euler this idea of doing this sum. I'm going to explain in a minute. This is a very unnatural thing to do. Why would you do something like taking alternating sums of something like this across different dimensions? I'm not going to give it away. I think many of you will know the answer, but there is one natural mathematical structure that exactly involves this. And Euler tapped in is exactly that, and that's the beginning of the index theorem. So let me go into that in a minute. So this is fun. You take any convex body in 3 dimensions, you're going to get 2. Okay. So now let me give you the definition of a convex polytope. So this is anti-Bourbaki. So now I'm going to give you a convex polytope. There are 2 definitions. I want to give this definition because we'll actually use it later. One is called the vertex representation. The other is called a half-plane representation. So the first definition, see, it's not even legible, so don't worry about it. You define a convex polytope to be the convex hull of a set of points which we call vertices. See if you can read the green, which I can't, but it's just formal sum of points up to some coefficients alpha, such that the coefficients add up to 1. So that guarantees there's no kinks. That's a bit funky definition. There's another one called half-plane representation definition, which is a convex polytope in any dimension is just the linear set of linear inequalities. Take a matrix H dot X less than or equal to B. If you were equal, it would be hyperplanes, or solutions of hyperplanes. But if it's less than or equal to, it'll define a convex polytope. So these are 2 inequivalent definitions of this. So in dimension 3, if you did this trick for a convex polytope and did this very strange sum, you're going to get the number 2. Okay, that's the first one. This is Euler, pure topology. Right? The proof is given by pure topological. It's combinatorial. There's a slightly sexier way to say it. There's always a slightly sexier way to say what I've just done. And I will allude to this. So what is so special about convex polytopes is that you can put the vertices on a sphere. Okay, so, and then what you're essentially doing is saying that S2, the sphere, is connected, so there is only one class of the point. The point is a dimensional 0 object, because every point can be connected to every other point. So there's essentially only one equivalence class of the point. It is simply connected, so any loop on the surface of a sphere is contractible. Right? So that's essentially saying that there is no class of the loop. And there's one class of the sphere itself. So 1 minus 0 plus 1 is 2. So what you essentially, what Euler was realizing is that convex polytopes, which can be drawn onto the sphere, can essentially be deformed into this sort of statement. He didn't make this point. The idea of the class did not occur to him just yet. I will get back to that in a minute. So this is the fancy way of saying it now. Okay, we're getting there. So you do alternating sums across the dimension. In other words, what we call Betty 0, Betty 1, and Betty 2, you should do Betty 0 minus Betty 1 plus Betty 2, and that's 1 minus 0 plus 1 is equal to 2. This is a very interesting fact. Now let's consider spaces that have this property. These spaces are called Eilenberg-MacLane spaces. So let's think about shapes, right, that have one class of the point, nothing in between, everything's contractible, and one at top dimension. Okay, so these are called EM spaces, Eilenberg-MacLane spaces. So the sphere is a perfect example. It has one class of the point, nothing in between, everything in dimension 1 is contractible, and the top dimension is the class of the sphere itself. The 3 sphere, the 4th sphere, they all have this property, right? The famous Poincare conjecture is the statement that the 3 sphere, S3, is the only Eilenberg-MacLane space. And that took 150 years to settle. So it's a highly non-trivial state. I mean, I can imagine lots of spaces that have Betty numbering. This is what's called a Betty table, you know, that have this property, 1, 0, 0, 0, 0, 0, 1. It's such a simple statement, and it took 150 years and a Russian crazy enough to prove this. Right? And you know, you have to be Russian and crazy to prove it. Not either is not enough. So that's the heart of the Poincare conjecture. That S3 is the only Eilenberg-MacLane space. Fine. Now you can, for those of you who've fallen asleep, this is 2, it's great. I'm going to tell you 4 ways to compute 2, right? So 2, then let's do the second way. Now I'm talking about spheres, because I can embed my pure topological computation of polytopes into a metric computation. Okay? So let's consider the sphere as 2. Okay? Well, there's a very standard metric of the sphere. This is the one that we learned when we were in kindergarten. This is the round metric on the sphere. Right? You know, even in theta phi coordinates, the sine squared theta comes from the Jacobian. Right? So that's the metric on the sphere. And then you grind through what we've been always taught in GR or whatever, how you've been taught. I can't do this. This is, you know, you write the Christoffel symbols. Right? You just plug it in. Plug this in. I'm not going to do this. I'll get it wrong. But my differential geometry professor as an undergraduate called Christoffel symbols Christoffel symbols because they're Christoffel. I mean, that was horrible. Like, you know, these 4 indices, you plug it in, right? You plug this in, and then you compute the Ricci 2 form, the Ricci, right? I'm not going to do this. Plug in. I did this on Mathematica. You just plug this metric in. This is 1, 0, 0 sine squared. Plug it into the gamma symbols. Right, you get this. That looks really nice. So the Ricci, the RIJ, the Ricci, the curvature is this 2 by 2 matrix. Right, and then we're told in GR to contract this matrix with G mu nu. Right, so you take this with the upper G mu nu, inverse G mu nu, and you see everything cancels out. It's 1 plus 1 is equal to 2. It's such a clean calculation. So what am I trying to say here? This 2 is, what does this say? It says that the curvature, the Ricci curvature of S2 is constant everywhere, and the value of that is 2. In particular, well, this is a very special case. If you integrate the 2 on the whole sphere and divide it by 4 pi, you're going to get, well, the volume of the sphere is 4 pi, so 2 times 4 pi divided by 4 pi is 2. Okay? Okay, I mean, it's stupid, but but it's 2. It's 2. Okay? Now something very deep is going on. The statement then is, if you take this computation, take any metric, you run through this computation, don't do this by hand, you'll cry, and then do this contraction, do this integral, over whatever you think you're integrating, divided by 4 pi, that's normalization, you're going to get 2 for anything that's like a sphere-like object. Okay? So where does this come from? This should be attributed to Gauss. So 1828. Look at the dates are beautiful, right? 1736, 1828. And Gauss, so I cheated a little bit. Gauss did not phrase it exactly in this language. Gauss called this fact, this integral, he called it his Theorem egregium, his great theorem. This is Gauss's great theorem. Of all the things that Gauss has done, he thinks this is his best work. Just that this integral gives this, and it's quite deep, right? An integral, which is a purely analytic object, should give a purely topological result, right? And it's equal to the number 2. Gauss phrases slightly differently, so I'm just going to quickly go over it, and you can just pass out for 30 seconds. Back in, when you studied differential geometry, remember, oh yeah, Gauss didn't have Ricci curvature and all that stuff, right? But this is modern language, right? So the way that Gauss phrased it, which is what we now call Gaussian curvature. Remember, for surfaces, you can have 2 curvatures, the 2 principal curvature. The one that's for like maximal, one is like maximal bend and one is minimal bend. And one over the product of the 2, the principal radii. And then he did the integral over this one, and he showed that the angle sum of this over some triangle drawn is some internal sum. But this statement that Gauss did is equivalent to what modern notation would say. Just you integrate the Ricci curvature divided by 4 pi. This theorem is now together with this part of Gauss contribution is known as the Gauss-Connect Theorem. Okay. And the date for that is 1848. This is a very interesting fact. He had to wait for 20 years because Bonnet was a student of Gauss. And Gauss never published this Theorem egregium because he couldn't bother. In fact, Gauss hardly published anything because he just couldn't bother. It's gotten to the point that every mathematician in the 1800s would write a letter to Gauss and say, by the way, do you have this result? And almost 99% of the time they'll go, oh yeah, I just did it last week and it's just trivial. Including great ones like Sophie Germain. Sophie Germain wrote to Gauss and Gauss was impressed. And that's one of the very few people who ever impressed Gauss. And she was a woman, and at the time she wrote as a man because she thought she wouldn't be taken seriously. As a woman, so Gauss really was impressed with Sophie Germain's work. And later on, because of, I won't tell you the story, somehow it involved prisons and Napoleon, and they found out, wait, this is a woman. And he was so totally blown away by how brilliant Sophie Germain is. Anyhow, 2, okay? That's the second way. Analysis with topology. You can almost imagine that this could happen, right? Almost. I'm going to get you more and more surprised. By the time, I was blown away by the 4th way to do it when I was a PhD student. I was so blown away, I was crying for days. So, let's do something a little jazzier, okay? Let's do a little bit of jazzier stuff. So I've gone through Euler, Gauss, and of course the next greatest person is Riemann. So how did Riemann contribute to this side of the story? Well, Riemann's greatest contribution to this story, I mean, Riemann has so many great contributions, but Riemann's great contribution to this one, I mean, you can see the dates, right? 1736, 1828, 1848, 1860. So what did Riemann do? Well, Riemann invented essentially what we now call complex analysis. Right? And Riemann's insight was the sphere is complex. is not just a real surface. The sphere S2 has complex structure. And now we're inching towards what I'm going to be telling you later on, which is Calabi Yau. So what is a complex manifold? Well, let's have a look. First of all, the sphere is a manifold. Right, this we can do. Everybody needs to check through this once. Okay, I'm going to actually do it once for you. So, as a manifold, I have to show that it is patched up by patches which are locally Euclidean. In fact, locally R2. Right. It's actually quite interesting, you know, to show that something is a manifold is a bit of a work, because you have to show that it consists of so many patches, and the patches patch together by differentiable function, right? This is why I do algebraic geometry. This is too sick. In algebraic geometry, the definition of S2 is one line. I will show that in a minute. But first, I will just show you that S2 is a manifold, okay? Everybody's happy with the definition of manifold, right? Raise your hand and just stop me if you're not. So you're not happy, okay? So I'm giving the definition. So like, this is a very interesting story, right? So this is great. I can turn this into 7 lectures. So apparently, Gauss killed Riemann. Well, at least this is what's told to me by my undergraduate differential geometry professor. So how did Gauss kill Riemann? Story goes, I mean, this could be entirely apocryphal, but at least it's partially correct. So when Riemann was up for his professorship at the University of Göttingen, okay, this is, you know, you have to do this extra habilitation in the German system. When you become a full professor, they will examine you again. Thank God they never did this to me, man. I'll fail. So you do 3 propositions. You propose 3 problems, and you defend it against, you know, a tribunal. Right, okay, fine. So Gauss happened to be one of Riemann's examiners. Can you imagine yourself as a fly in the wall in that room? This is Gauss examining Riemann. So Riemann proposed 3 problems. The first one is, of course, what we now call the Riemann hypothesis, which is just thinking the Riemann zeta function. I will get to the zeta function in a very surprising way. The second one I don't remember. But the third one, he said, oh man, I can't think of a problem I can do. How about the foundations of geometry? Because he was, one of the problems he was thinking on the back of his mind. So he proposed these 3. But Gauss, because he was thinking about his theorema Grigio, he was thinking about geometry, non-Euclidean geometry, what we now call Riemannian geometry, right? Or Gauss-Riemann geometry. He says, I want Riemann to do his 3rd problem. I don't care about the Riemann zeta function. I want him to do this geometric problem. And Riemann got back and he says, oh shit, I haven't thought about this at all. So he worked day and night to write essentially from scratch the foundations of geometry. Can you imagine, right? And then got his professorship and died within a month of tuberculosis at the age of 39. So he worked himself so basically Gauss worked Riemann to death with that problem. And that problem essentially is now what we call the definition of a manifold. So why was that problem so important? Is how do you define a space intrinsically without embedding, right? And I'm going to go completely the other way for the rest of the lectures, which is I'm going to go through the algebraic geometry method, where everything is about embedding, because it's easier for me. But this problem is how do you define a shape intrinsically without reference? You know, S2, we think about S2, but we're biasing ourselves already. We think about S2 as being embedded in R3, right? X squared plus Y squared plus Z squared is 1. Or, you know, cosine theta, phi sine theta, you know, whatever that, right? That's all, there's an embedding to that, right? But how do you define S2 without embedding? Well, the only way to do it is to say, well, S2 is locally R2, right? As every manifold must be, or any such a shape. So, and how many, so can I put an open cover of sets, each of which is a copy of R2, and then I'm going to glue them together in some nice differentiable transition function, and then if I can find that, then that's what defines S2 for me. Okay, so for example, S1. S1 is a circle. How do I see S1 as something that's not embedded? Well, that's very easy, because I can take S1 like this. I remove the south pole. Then it's just a line. It's R1, right? That's one patch of it. Well, then I can also remove the north pole, which is the other one. And then these two glued together essentially by the trivial function is theta, the angle. So that shows that S1 is a one-dimensional real manifold. Okay. So now I'm going to jazz that up a bit and use the one that's not usually done. I'm going to show you that S2 is a manifold using stereographic coordinates. What's called stereographic coordinates. This is not the one that you usually learn, because you can imagine I can also do like theta and phi coordinates, right? So the reason I choose to do stereographic is the most beautiful thing, which is on the next slide. Okay, you ready? Ready? And this is it happens once, only once. Okay, you ready for this? So let's take a sphere, S2. I'm going to take the north pole and I'm going to project onto a line, a plane at the equator. Okay? So what I want to essentially say is that S2 consists of two patches, one of which is the upper hemisphere, and that's clearly it can be put into 1-1 correspondence with the plane, therefore it's R2. And the other one is from the south pole, and it could also be put into 1-1 correspondence with this plane. And these two meet perfectly in the following sense. Okay? So let's look at the north patch. I'm going to take the stereographic projection from this point. It'll pass through x, y, z, and it will hit a point which I call x north and y north. Two coordinates. Okay? And then some simple trigonometry, which I can no longer do because I'm too old, shows that just by similar triangles, the north coordinate is little x over 1 minus z. This is a unit sphere. So x, y, z is a point on the sphere in the northern hemisphere, and just by similar triangles, it'll hit there and hit this point x north, y north, and the x north, you can clearly convince yourself it's x over little 1 over z or y over 1 minus z. Okay. Similarly, I can do the south patch, which is I take a point here, I join one line to a point on the southern patch. It'll hit exactly one point on this plane, and you can see that you can just convince yourself that it's plus just by similar triangles. So I've shown you that S2 has two patches, each of which is in 1-1 correspondence with R2, the Euclidean plane. Okay. So now let's think about something totally crazy. Okay, this is crazy. Okay. I'm going to show you that the transition function between these two to this two is not just differentiable, C infinity, but it is analytic. It's an analytic complex function. Okay, so let's see how that's done. Well, it's very simple. Let me define a new coordinate, capital Z, which is x north plus I, y north. Okay, because Riemann likes to put I in it. Okay. Then I'm going to have another coordinate W, which is x south plus I, y. Sorry, this is a typo. This is a south. Okay, then let's look at what the transition function is. Okay. This transition function, W, is, okay, just compare these two, right? How do you go from here to here? Well, it clearly is just little x minus I y over 1 minus z, which you can factor out to be 1 minus z plus 1 plus z times this combination with the complex conjugate. This is a complete accident, and I will show you in a minute this is a complete accident. And then you can rewrite this, and lo and behold, this is 1 over z, which is an analytic function. There are no bars, there are no z bars. So what have I shown you here? I've shown you that S2 is in fact a complex manifold. It's complexifiable because I've made this not just identifiable with R2, but because of the I I've made it identifiable to C, the complex plane. And likewise here, sorry, this is an S, to C. So what S2 is now, it's two copies of not R2, but C. And they're packed together in this transition function. One coordinate is on the complexified northern hemisphere, and the complexified southern hemisphere, and the transition function is analytic. There are no, holomorphic if you wish, there are no bars. So this argument shows that S2 is not just a manifold, but it is in fact a complex manifold. So that's Riemann's contribution. It's a very nice way to see this through this projective coordinate. I mean, this stereographic coordinates. Why do I want to emphasize this? Okay, you remember this now? Punchline, if you're passed out, just remember the take-home message. S2 is a complex dimension 1 complex manifold, right? Because it's locally not just isomorphic to, homeomorphic to R2, but it's locally homeomorphic to C, right? Because R2 is not C. You need to put this extra complex structure. You can multiply with an I in it, right, to make it complexifiable. Okay, forget about everything I said. You know, every 2 slides, forget about everything, and then I will patch it together. Now I'm going to show you what a complex projective space is. Okay. Again, I'm going to go with the Bourbaki approach in the beginning, and then we'll do the anti-Bourbaki. Okay. CPN is Cn plus 1 quotiented by the equivalence relation that x in Cn plus 1 is to be identified with a non-zero complex number that's to whatever, right? Okay, that you're gone. At this point, if you tell this to a graduate student, it's over, right? So let's see what CPN really is, okay? So if you look at RPN, this is very important, right? Let's look at R3. We live in R3, right? Right. What is the single most important piece of work that started the Renaissance? Yes, the perspective, the point at infinity. If you look at pre-Renaissance paintings, just go to the National Gallery. Any pre-Renaissance work, it's flat. Renaissance, Da Vinci, pre-Da Vinci. I think the first one is Piero della Francesca. Somehow he made a point of convergence at infinity. So in other words, that first painting, I think it is is that in the British Museum or in the National Gallery? I can't remember. That painting is the first painting to ever be done in RP2, not R3 but RP2, because he added a point of infinity. Okay, so now let's define what that means. So R3 we're happy with, right? This is R3, we live in R3. But consider the set of directions in RP3, in R3. So what does that mean? That means let me identify every point in R3 with anything that is equivalent, that is a non-zero multiple of that point. But that's what it means, the set of directions in R3. So instantly you contract all of R3 down to at least the sphere, because everything is equivalent by scaling, and then you can even identify antipodal points. What does that do to you? It brings out the point of infinity, right? Because the point of infinity is now just into anything in a finite distance. So RPN is already compact by bringing this point of infinity. Well, CPN is just the jazzed up version of that, right? It's the complex. So you take, let's do it properly, you take Cn plus 1, right, with n plus 1 coordinates, complex coordinates, and you identify anyone, you can't draw this anymore, this is already complex. You identify anything that's related to each other by scaling, by something non-zero, and you do this equivalence relation. So let's take an example. Let's take CP1, my favorite complex manifold. Okay, that's what CP1 does. You take C2, I told you to CP1, so n is equal to 1. You take C2, let me consider the two complex coordinates of C2, x0 and x1, they're complex. What do is, I establish the equivalence relation, that x0, x1 is equal to a non-zero complex number multiplied by x0, x1. Okay? In other words, every time I can scale out a multiple, it's the same point under this. Okay? Now, I'm going to show that CP1 also has two patches, and it is holomorphic transition function, and we'll see what it is. Well, it's very simple. The two patches of CP1 can be taken as follows. Let's consider x0 not equal to 0. That's the first patch. And let's consider the second patch as x1 not equal to 0. Okay. Well, in the first patch of x0 not equal to 0, I can choose a good coordinate, which I'm going to call capital Z, which is x1 over x0. Because x0 is not 0, I can divide it. On the other hand, the other patch is when x1 is not equal to 0, my good coordinate is w in this ratio. Now, this explicitly shows that this patch is homeomorphic to C, because this is a complex number. It's a well-defined complex number. So I have two patches, each of which is a copy of the complex K. Right? And explicitly given by this coordinate and this coordinate. Well, what's so cool about these two coordinates is this is the reciprocal of this. So, in other words, CP1 is a complex dimension 1 manifold with transition function which is holomorphic, like this. I've seen this before! It's exactly S2. So Riemann's great realization is that CP1 is topologically homomorphic to S2. This is an incredible realization because it never happens again. No other sphere in any higher dimension will ever have this property. No, S2n, you think, oh yeah, maybe I can complexify. I mean, look at the trick that's needed to complexify. I mean, there's a lot of miraculous cancellations here, right? All the conjugates have to cancel out. If you try to massage S2n, where n is bigger than 1, to try to make this, just won't work. So S2 is the only complex manifold for n. But they're not even complex. You can't do this. And in particular, S2 is topologically CP1. We're going to use, so this is in some sense, this has been used over and over and again in algebraic geometry. When in algebraic geometry, when we say you blow something up, right? You don't mean to you don't use dynamite. You use this fact that you can put a so this is called a projective line, obviously, because it's complex projective 1, so it's called a projective line. And then this projective line it's homomorphic to S2, so you can blow up points in this particular way. But that's later. This is an advertisement for later. Like, so cool, right? It doesn't happen again. Like, when I saw this fact, I was kind of blown away. Like, it's so cute that S2 is the only CP. Right? It has this very strange property. As CP, this is a complex projective line, and then this could happen. You know, there's CPn, but none of them ever has the structure of Sn. Okay. Okay, forget about everything I said. Okay, I'm going to get the number 2, the third way. Maybe I'll pause to give you the fourth way. And that was completely good. When I saw the fourth way, I'm just building this up. So this one is, look at the dates, right? It's perfect. This lineage, 1736, 1828, 1848, 1860, 1865. So this is very simple. Because now S2, because of work of Riemann, is a complex manifold, CP1, I can do holomorphic functions. I can use complex analysis. Right? So let's do a complex analysis on this. Well, the transition, this is cute. I mean, I'm not going to explain too much on this, but at least this is a consequence of something. The transition function, remember I told you, is this analytic holomorphic transition function, w to the 1 over z. Right? Well, let's consider dz. the one form dz. Well, I can just, this is such a cute computation. dw is d over 1 over z, and so it's minus 1 over z squared dz. So the transition function is 1 over z, but this form, dz, this differential, how does this differential transform? It transforms 1 over z squared. This is just, I don't know, taking the derivative. This 2 is the same 2. It's the same 2. So this is what's called a degree 2 transition function. If you want to get really sexy about it, which I won't get into, this differential this one form dictates the transition of a particular line bundle on S2. And the degree of the line bundle is 2. So the sexier way to saying this is that CP1 is, as S2 is complexified into CP1, and the degree of the anti-canonical line bundle has degree 2, and that 2 comes from this derivative. Of course, I haven't defined for you what anti-canonical line bundle is, but just take it because it's such a sexy word. Just like go home and impress friends with it. But that's all I'm going to say about this. So this is a consequence of Riemann-Roch. The essence of Riemann-Roch is to realize why the degree of this transition function can be controlled by something directly from the topological properties of CP1. So 3 ways now, right? And I'm going to finish here so that I'm going to, okay. How am I doing on time? Can I take?
Maybe a 5-minute break now?
You want to take, yeah, have I gone on for 45 minutes? Okay. Yeah, I think I'll wait. Yeah, okay, fine. So to advertise, the 4th way would be after this break. And I promise you, if you haven't seen it, if you've seen this for the first time, the 4th one completely blew me away. This you can almost imagine, right? This is 150 years of geometry. You can imagine topology being related to differential geometry, to sort of degrees of transition function. That you can almost feel that's possible. But the 4th one is so mind-blowing. I'm giving great advertisement. It took Grothendieck to settle half of it. Right? And this is Grothendieck. So, yeah, anyhow. So take a break and I'll come back. I'll mention a little bit. So far everything I've done is differential, right? I haven't mentioned about embedding. I'm going to mention a little bit about algebraic geometry in the next bit. And then I'm going to totally blow your mind. Okay, you just get ready for get yourself a coffee, like get psyched up on it. Go chill. Thanks. You clapped well, thank you. So it's funny, during the break I took some people here to my office to prove that I actually do have Bourbaki, that I just worship like and I'm not worthy. But it's just too difficult. It's like reading Bourbaki is like, reading like, it's like, I don't know, you imagine reading Bourbaki is like you're very devoutly Jewish and you try to read the original text without all the Mishnah in between, so without interpretation. It's just too much. It's too intense. Anyhow, so now let me just give you algebraic geometry in 2 slides before going on to the 4th way to get to number 2. So, as we saw, defining manifolds is actually really difficult. Right? You got to get the patches and get the transition functions. I show the transition functions infinity if it's a real manifold, or it's analytic or holomorphic if it's a complex manifold. But algebraic geometry is much easier. People, I don't know, like in grad school, you always learn differential geometry first before the algebraic geometry, right? But that shouldn't be the case. You should be exactly the way around, because everybody's done algebraic geometry since kindergarten. Like when you were 5, the first thing you were told was x squared plus y squared is equal to 1 is a circle. That's an algebraic variety, right? I'm just giving you a real algebraic variety in R2. That's it. So let's think about CP1, which we know is a manifold, as an algebraic variety. Here's something that's really fun. In French, in the original, in Bourbaki, it's maximally confusing, because manifold in French, I believe, is variété, and an algebraic, a variety in French is variété algébrique. And same thing in Spanish and other, but somehow in English we created a new word, manifold. Well, I like it in English because also in Chinese, you have one class of things for manifold, which is an analytic object, and variety is a purely algebraic object. Right? So they're two different things. So, what is an algebraic variety? Very simple. All it is the vanishing locus of a set of polynomials. That's why it's called algebraic. Right? So that's it. So what would mean? That seems pretty odd, right? But the great theorem of Nash, if you think of Nash as like the Nash equilibrium, right? That's not his greatest contribution at all. You mean you just get the Nobel Prize for it. But Nash's greatest contribution to mathematics, that's like a minor thing. He probably did like in one afternoon. Nash's great contribution is to show that every manifold defined in this patchwork way can be realized as an algebraic set for some high dimension. So that's the Nash embedding theorem. In other words, the class of all manifolds you can think of as algebraic varieties. So that's why we do this. And the dimension is very high. So we showed, I think, a manifold of dimension n can always be there exists, I think, 2n plus 1 or 2n squared plus 1 variables in which you can realize your manifold as the vanishing algebraic set, so a set of polynomial roots. So apparently, this is very interesting. So the guy who taught me algebraic geometry, a great guy called by the name of Gerhard Waschnitzer, who this guy's a legend. So he got tenured at Princeton at the age of 27 in 1968, and his last published work was in 1969. that's what tenure. I mean, he did absolute jack from 1969 until when he told us in late 1990s. He just hung out. But he's a font of wisdom, and he's a fun guy. And he would just I remember this, like his differential geometry lectures were like, I have no idea what he's talking about. It's just basically most of his lectures. I think I learned a lot of his lecturing style. Most of it is about how great Gauss is and how much a jackass a Karl Marx was. So most of his lectures was like, Gauss is great, Karl Marx is an asshole. And he would just use these words. And somebody dared to challenge him. Somebody, I think somebody questioned him about like Marx or something during one of his differential geometry. He says, well, screw you! And like in the lecture, and then by the end of the second week, there were only 4 of us left, and we've all become professional mathematicians. Because we were like, what the hell is going on? But anyway, so Waschnitzer was good friends with Nash because they grew up in the same generation. And he told me that, he says, forget about Nash equilibrium. The Nash embedding theorem is his greatest work, which is true. And it's what drove him completely crazy. He said the day after he proved the Nash embedding theorem, it's a simple theorem to state, right? Every manifold of dimension n, there exists, and I think n squared plus 1 coordinates in which this manifold is an algebraic set in that dimension. After you prove this, and the embedding is isometric. It preserves distance. They exist in an isometric embedding of this manifold to this high dimension as an algebraic variety. And he said, after he proved it, it was like a 250-page proof. It covered one entire volume of Annals of Mathematics, like Andrew Wiles' proof of Fermat, right? And then he said he was never the same man again. He went completely nuts. So that's the true story behind the beautiful mind. It's this particular theorem, that the fact, not just CP1, but every manifold is an algebraic variety. There exists some embedding. Okay, but we don't have to go crazy. We can do CP1 because this is baby version. It's very simple. So let's show that CP1 is not just a manifold, but actually an algebraic variety in the sense of vanishing loci of polynomials. That's very simple. Because let's consider the embedding C into C2. Well, this is very simple. This is just hyperplane. Or in fact, I can just write it like this. This is a hyperplane in 2 complex variables, x, y, and z of C2. And I define a linear equation in two affine variables, complex variables x and y. So it's C. That's it. But that says C inside C2 is defined by this hyperplane. Well, I told you that C added to a point is CP1, and C2 added to a point is CP2. So this embedding is just projectorization by adding this point at infinity. So CP1 inside CP2 is a degree 1 homogeneous polynomial. Done. Because it's a trivial polynomial of degree 1. So that shows that CP1 is in fact an algebraic variety, and it's embeddable into CP2. That's it. I mean, nothing fancy. I'm just saying, well, in other words, you can just do it. I mean, you can even probably plot this, right? I can't think. I mean, you can plot this in mathematica. Do CP2, do the 4 coordinates in CP2, eliminate one of them by projection, and then do a hyperplane in that, and then just plot, like, I don't know, Monte Carlo it, and you'll see that it's somehow should be. I've never done this, but you do it. So that's great, right? Awesome. So a hyperplane in CP2 of degree homogeneous, degree 1. So why do I say homogeneous? Because inside, remember, inside projective space, I have to make sure it's homogeneous. Otherwise, the ratios won't work. For all the coordinates must have the same degree. So here, x, y, z. So this is a polynomial. This is a homogeneous polynomial of degree 1, where alpha, beta, gamma are coefficients that define this polynomial. So these coefficients are called complex structure, and they define the shape. So of course, as far as this algebraic geometry is concerned, this doesn't just define a sphere, it defines, an ellipsoid or any elongation thereof. And how far you stretch it, at least they are topologically S2. So how much you stretch this will be governed by these coefficients. Okay. So that's one. So this is a take-home message. A degree 1 homogeneous polynomial, otherwise known as the projective line, inside CP2 defines for you CP1 as S2. Okay. Well, let's just bump up a degree. Let's just go up in degree. What about degree 2? What about a degree 2 polynomial, homogeneous polynomial, in 2 complex variables with 6 complex variables, we can factor out 1, 5 complex coefficients, complex structure. What should this define for you in CP2? So this is a little harder to, of course, you can keep on going, right? So this in algebraic geometry, these are called plane curves. This is a horrible name because curves are complex 1-dimensional objects in algebraic geometry, but complex dimension 1 is real dimension 2. So when in algebraic geometry, when you say a complex curve, you mean a surface, a real surface. So this is a horrible name. So they're called algebraic curves. So algebraic curves are also known as Riemann surfaces because Riemann surfaces carry complex structure. So they're surfaces. As a whole, I don't know, maybe it's better in French. I don't know. It's also called French in curve. It's called, probably? Yeah. Algebraic, or whatever. Yeah, it's horrible because you have to think in dimension. They're not curves. I mean, they're surfaces. They're just called complex curves because this for me is a complex curve because it's a single polynomial, right? That's 1 degree freedom inside CP2. So 2 minus 1 is 1. So any single polynomial is known as a hypersurface. This thing inside CP2 is realized as an algebraic complex curve, which is equal to a real manifold of dimension 2. So that's just a linguistic issue. Just multiply by 2. So I've already shown you that a single linear polynomial, the trivial hyperplane inside CP2 is CP1. But what about a degree 2 object inside CP2? Well, this you should already recognize from kindergarten because we have seen something like this. If I told you x and y and z are not complex but real, and I wrote this not inside CP2 but in R2, these are conic sections, right? These are exactly the complex generalization of the conic sections. That's what conic sections are. They're degree 2 polynomials. The most famous conic section is the circle. Take alpha equal to 1, beta equal to 1, gamma equal to 0, everything, and set the last constant to be 1 or something like that, right? That's the circle. That's the most famous one. So the degree 2 homogeneous algebraic variety, as an algebraic variety, algebraic curve in CP2, is the complexification of conic sections. So I should at least get a slice. I mean, this is a surface, right? So you embed this polynomial in CP2, there should exist some kind of a cut where you would see the conic sections, right? Somehow. I'm not going to tell you how to find this cut because I don't know it's getting too complicated, but right, I mean, it's the complexification of the conic sections. So, but back to this question, but what does this thing give us topologically, right? I told you this one is topologically a sphere. This one is topologically a what? It's very hard to visualize, but then Riemann comes to the rescue again, because this is before he died at the age of 39. It's good not to die at the age of 39, but well, no. So Riemann had a very beautiful way of visualizing complex polynomials in complex variables. And of course, this is a trick we do remember from complex analysis, right? Which is the trick of branch cuts. So let me go back to C2, because I can't really work in CP2 anymore. I'm going to go, just remember there's a point at infinity. So I'm going to go back to C2. Sorry, whoops. Yeah. So I claim I can write in two complex variables, y, so it doesn't have to be homogeneous anymore. Right? Y squared is equal to some polynomial of the degree n. Okay. We've learned that in the degree 1 case, or the degree, well, if the trivial case of y equal to degree 1 is S2, topologically. The one we want to study is more general. Let's consider y squared equal to some nth degree polynomial in a complex variable. Now, how do I visualize this? Right? In particular, let's take px of degree 2, right? Because that's the one, that's the complexification of the conic section. So let's look at this degree 2 polynomial. Well, here's a variable of one variable, and it's over the complexes, so I can completely factorize it, assuming no multiplicity roots. This is why we do complex geometry, because this trick would not work over the reals, and that's why real algebraic geometry is so much harder than complex algebra. And this is the point about Riemann thing is that everything becomes nice because everything is factorizable because of the fundamental thing of algebra. So you got this thing. Let's just factorize to n roots. Let's not worry about, generically you won't have multiplicity of roots. So Riemann gives this wonderful. I don't know. It's Riemann. I don't know. We're not worthy. So at all the roots, right? It's at the roots of this polynomial, it's 1 to 1 because you have y squared equal to 0. Right? But at all of the other points that are not the roots, it's 2 to 1 because it's y squared is equal to something. You have plus minus root. So this is what's called ramification. This is what's called ramification index 2 here, and this is ramification index 1. So Ed is nodding because we do descent d'enfant. I've got to tell you about descent d'enfant. Oh my god. Okay, lecture number 15. I'll tell you about this is like the most amazing thing. Another thing that totally blew me away. In fact, I've got to tell you descent d'enfant, but later. So in our quadratic case, y squared is the quadratic in x. So it's 1 to 1 at the roots. And then you've got this branch cut in between the roots on this complex plane. And then you've got to paste the two, where along this branch cut between these two roots. I mean, this is a standard way with what we taught, like in complex analysis, and third year complex analysis. But if you look at what this is happening topologically, because I've added a point at infinity, right? So my complex plane is actually a sphere, and this complex plane is also a sphere, and then I'm gluing along the two branch cuts. When I glue it, I get a sphere. So in other words, the quadratic in CP2 is also topologically a sphere. You say, oh, well, that sounds so trivial, but I'll show you. Just stay with me. The upshot is that as you go up in degree, it goes in twos, in pairs. The higher degree polynomials, you'll start to see more interesting structure. So, bottom line, the degree 1 and degree 2 homogeneous polynomials in CP2, okay, so this is the long-winded way to say it. The sexier way we can say now, because we're so cool, is the algebraic variety as a plane algebraic curve in CP2 of degree 1 and degree 2 are topologically spheres because of this Riemann pace. And you see where I'm getting. You can think about degree 3, degree 4, degree 5, degree 6, and those will actually start creating more and more holes, which we'll get to in a minute.
But in degree 2, we didn't look at the most general case, right? We looked at y square equals px kind of thing.
Oh yeah, but I'm saying that, yeah, good. So yeah, so you can trust me that in CP2 I can put everything into this form by sufficient transformation. So this is what's called the hyperelliptic curve, hyperelliptic form. When you write y squared is equal to single polynomial. Trust me, you can do this massage to bring the general conic section to this form. It's highly non-trivial. Even degree 3 was highly. I think we were playing this right, JK, and we wanted to like cry. Just putting it. Just think about this. And the claim is that the general homogeneous cubic can also be put after sufficient transformations that involve nothing but rational functions to something of this hyperelliptic form. Okay, so that's good. So this is upshot. Well, you can almost see this, right? Because S1 embedded into R2 is this, right? This we know from kindergarten. Is the real slice of CP1 and CP2, and that's the one slice of one radial crater of the circle. So the fact the circle is the real project. This is the slice that's been put. At least in this case, I can do it. This slice, or the ellipse, is the slice of one of the slices of this sphere. Right? You can write in this embedded. This is the two. This is the double of this in the sense of complexification, and you can see. Right? This is one longitudinal line or latitudinal line inside here. Okay. So now we've just done. That's all that we've just done algebraic geometry in a completely non-Bourbaki way. Right? Like, but this is fun, right? When we were doing like this is how it's supposed to be done, and then you can tell friends. So like I'm beginning to think like the Bourbaki school is like you play with this in private, like here, and then you go tell your friends in a sophisticated way. Let X be an algebraic scheme over whatever. Oh, do you know about this story? This actually happened. This was so bad, it got into this point in the 1950s, 60s. Gordon Geek invited somebody over to give a lecture in Montpellier, and the guy says, let X be a manifold. Okay? And nobody in the audience knew what that was. They raised their hand. He says, I'm sorry, what is a manifold? And Gordon Geek turned around and says, oh, just think about this as a non-separable scheme over an algebraic closed field. And the guy says, oh, I see. And then the speaker was like, they've made it all completely higher algebraic and that, so abstractly algebraic. I know JK may appreciate this. JK is my student, he likes this very beautiful language. He's Bourbaki. I'm anti-Bourbaki. Okay, punchline. So that's cool. So we've done some algebraic geometry. Now you're ready for the fourth way. I'm going to get to number 2. Okay, you ready for this? Is completely mind-blowing. Okay, everything I've said so far is almost imaginable. The fourth one is so unimaginable, you had to wait until 1950s for people to settle him in and understand what it means. And I'm by no means an expert in this, but it was mind-blowing. The little glimpse I can understand the fourth method that I have to share it with you. And I think it's something that physicists don't usually see. So look at the number. So the last date was 1865. We've got to fast forward to 1949, And the works were 1960, 65, Grothendieck 65, and Pierre Deligne 74. So this is now in the 20th century, right? So anybody who's made this contribution's got the Fields Medal. That's how mind-blowing this fourth method of getting 2 is. Okay, you ready? Physicists usually don't appreciate this one because you're not taught this, but you have to. All right? Okay, I'm getting emotional. Okay, you ready? Now let's consider a smooth manifold X. Don't think about it as a non-separable scheme. I'm just thinking of a smooth manifold X over FPR. Okay, now physicists don't think about this, but it's important. So FPR is a finite field. So let's think about this, right? Let's go back. Finite field, so number theory in half of a slide. FP is a field of characteristic P, a finite field. So what is that? Well, it's just ZP, Z over P. So if you think of the cyclic group of P elements, right, you can also do addition, subtraction, multiplication, division in it. It's in other words, modulo P arithmetic. Right? That we physicists usually think of that as the cyclic group of order P, right? 1 alpha squared, alpha cubed, all the way up to alpha P minus 1. That this thing, but it actually forms a field, and the arithmetic over that is what we call modulo P arithmetic. It has to be prime because we can't, it won't form a field otherwise, right? If you do modulo 6 arithmetic, not everything has its inverse, right? Just think about it, right? I think I can't think of an example. Sorry, if you do modulo 5 arithmetic, it's fine because 5 is prime. If you do modulo 4 arithmetic, you don't have a unique, you can't divide uniquely. Right? This we recall from. Right? Everybody's happy with this? You need every element to be co-prime to this chosen prime P in order to have inverse. Right? So. Yeah, so whatever. So I can't think of it. So for example, the number 4 modulo 6 doesn't have an inverse. They're not co-prime. But the number 4 modulo 5 has an inverse, multiplicative inverse. I think what it is, 4 times. I don't know. 4. Good. Yeah. So that's fine. So this is a finite field, FP, and it has right. So in other words, modulo P arithmetic. It forms a field, not just the group. Okay, here's a theorem. All finite fields are isomorphic to P to the R elements for some chosen prime P, and for any integer R greater than or equal to 1. Okay, so how do I see that? The basic, the one-line sketch proof is, well, all you need to do is, so what are all of the finite fields of FPR? These are fields which are polynomials in one variable with coefficients done modulo arithmetic P, right? And of degree R. Okay, so you just think about all finite fields you can show are irreducible polynomials of degree R whose coefficients are done modulo P. You can do multiplication, and you can do addition, subtraction, and division, up to modulo this polynomial. So, okay, so that's it. That's all the number theory we need. This is the key. Well, so you see why this is surprising, right? So far we've done topology, combinatorics, geometry. There should be no relation to prime numbers. Right? This has nothing I've said so far should have anything to do with prime numbers. That's why it took so long, as late as 1974, for Pierre Deligne to show this using the Grothendieck. So don't trap me in the dark to try to give you a big explanation. This is too deep. So apparently Grothendieck had to invent what we now call L-adic cohomology in order to get this control over this. But I'll show you anyhow. So, but you agree with me now, I just need this one key fact. is that all finite fields are of the form are fp to the power of r. Fp for short, that's just arithmetic modulo p, but in addition, you are allowed finite fields of any power, of any prime power for a chosen prime. So they all form fields. And you can see that because that's just polynomial arithmetic modulo some degree r polynomial, up and with the coefficients. Okay. Okay, this is nice. Okay, we're ready. Okay, so this is the genius step, I think, of Dvorak. Let me define for you a local zeta function, and I'll explain to you why this function is called a zeta function. Well, it's a generating function. You know, we're physicists, we love this, right? So let me take your smooth manifold or smooth algebraic variety X, because every manifold is an algebraic variety. I'm going to count when I put this variety not over C, not over the complex numbers, of which there's infinite number. For example, if a manifold has an infinite number of points. But if I define this over a finite field, then there's always a finite number of such points. Okay, I'm going to show you, I will clarify this with an example in a minute. So I'm counting my X over these finite fields. Okay, that's a number, and I'm going to consider the following generating function in this very strange thing. You know, here's what it is. So order by order. You can think of this problem as follows. I said every smooth manifold by Nash embedding is some algebraic variety. So consider x cubed plus y cubed is equal to z cubed. You see where I'm getting with this, right? This is an algebraic variety. Over C, I know there are infinite number of points. But over each Fp, and I know over Q there are no points because of Fermat's last theorem. Right? And so you see where I'm getting with this. So, but consider the over Fp. Are there any solutions? Sure. No, consider the number of integer or rational solutions, rationalized denominator, consider the number of integer solutions x to x cubed plus y cubed equals z cubed over F3, right? And then F3 squared, F3 cubed, F3 to the fourth. In all of these, I can count the number, I just do a block search, a grid search of how many times this, it's a finite field, so there's a discrete number of points. How many of these will fall onto this variety, x cubed plus y cubed equals z cubed, and I can count how many times these points happen. I can't construct that right now because I need mathematics to give you explicit, right? Just count this number of points, but it's always finite because I'm doing a lattice search, right? This is a lattice, p to the r, right? We just think of p, this is a discrete set of points. So for every r, starting for a chosen prime p, so that's why it's called local. The local is because you localize at a prime p. For every chosen prime p, I can write down this generating function that counts the powers of this of this thing. Okay, so that's, and then you ask my question. So what's so special about any particular prime p? Well, nothing. I've just localized at a particular prime, and then you construct what's known as the global Hasselbalch zeta function. Well, you take product over all p. So you got your local zeta function localized at a prime p, and then you take a product of all p in this form, and then you do this very mysterious substitution. T is equal to p to the minus s. Okay. Well, I think already the astute members of the audience will know why I've done this substitution. It's because of because of Riemann zeta. So you will see in a minute. So now I will clarify this a minute. So this is the Euler product, right? I'm obviously going to get some kind of Euler product out of this very shortly. Phew! I've done exactly what I promised not to do. That was almost in the style of Bourbaki, because I'm giving you definitions. Okay, now let's actually give you an example to see what we're doing. Let's consider the simplest smooth variety. A point. Just a point. Okay. Well, the local zeta function says, well, if it's a point, it's clearly a point. There's a single solution, the point at every FPR. It's just the point. It's the point. That's my point. Right. So I can substitute 1 for all R, and I can do this sum. This, if I'm not mistaken, is summable. Is the sorry, did I miss the minus sign? I think this is just log. Right, log 1 minus t has this expansion. So exponential of the log is 1 over 1 minus t. Right, it's so simple. It's okay. This is nothing crazy. So for a point, the local zeta function is just 1 over 1 minus p. 1 over 1 minus t. Okay. So the global zeta function, the Hassadei zeta function, is take the product. I told you to take a product over this, and do this mysterious substitution. T is equal to p to the minus s, and do the product over all primes. So now we're not distinguishing any particular prime. And that, because of Euler product formula, is the Riemann zeta function. Yep? Happy? Not happy? Everybody's seen this step, right? The Euler product formula of all prime. I mean, to show this is very easy. You just take this. You do. This is a geometric series. So it's 1 plus p to the p to the 1 plus 2 to the minus s, 3 to the minus s, blah blah blah, and then 1 plus 3 to the s, and you do take all possible products. Because of unit factorization of integers, you get only one contribution of 1 over n to the power of s for an integer n, and that's the Riemann zeta function. And this is why these suckers are called zeta functions, because the simplest smooth variety, which is a point, the global zeta function, the Hassadei global zeta function, is the Riemann zeta function. Okay. Also, yes?
I'm not sure I understand what we mean by counting the solutions in FP. As in, what are these solutions? Because x equals a point.
Yes.
Right? Is this defined by some equation? Or
yeah. So yeah, good. So for this case, it's so trivial that my point. I'm really because I'm defining this over FP. The number of points that my variety has is actually discrete, and I'm just going to literally count in this the number of these discrete points. Yeah.
I guess I know, but I'm understanding correctly. Is you are not thinking of the manifolds itself, but as the equations that define, like the set of polynomials that defines.
Yes.
Then you look at solutions of those polynomials.
Yes, that's right. That's right. So here I don't even need, because it's just the point. But maybe the next example I can clarify. Let's do CP1. Okay, I think maybe that helps. Actually, this is also bad because CP1. Yeah, I'm not using the polynomial. In general, you're absolutely right. In general, I have to write down my actual polynomial and just find the number of points that solve this polynomial modulo, inside FPR.
yeah. But so the polynomial you're starting with would have coefficients in what? In FPR?
Yes, I will have to do everything in FPR. Yeah.
Okay, but then you have to count the number of solutions in FPR for different R's. So does the polynomial change in every step? Because I don't know if it makes sense. If you start by defining the polynomial with coefficients in, say, FPR, and then you need to count the solutions in FP1, do you have to bring the coefficient? It feels like you're counting the solutions in a different field than you have the polynomial in. So I'm not sure I understand.
I fix my polynomial once.
Yeah.
And then I consider, say, like 3x squared plus 4y squared is equal to 1, and I solve this in every FPR for chosen P and R. Yeah.
I guess maybe the original polynomial has coefficients maybe in Q that you can factorize to be in Z or something, and then once you're in Z, you can go down into FPR. Or Yeah, I guess. I know. Because
Yeah, I guess you mean I take these each coefficient and I have to consider them FPR individually.
Yeah.
But my next example is also cheap because I actually don't do the polynomial. It's just too hard to count as points. The next example is CP1, the one that was talking about, CP1. So this is CP1, right? Well, if I do CP1 again, I don't have. I should come up with a non-trivial example of of an actual polynomial where I count the roots. But maybe when I get 0, I will do this. I think. And let's consider CP1 over FPR. Right? Well, this is CP1 as a. Instead of considering CP1, I'm really just considering C over FPR, of which there are p to the r number of points, because they're discrete p to the power of r points. And I add 1 point for the point at infinity, because CP1 is C plus this 1 point at infinity. So in other words, my CP1, this count for CP, so a point is just 1, but for CP1, I'm considering CP1 not defined over C, but over PR, of which, and I know they're exactly p to the r number of points. But because it's CP, it's p, this is just C. But because it's CP, I have to add 1 for the point at infinity. Okay, that's it. So now let me find the local zeta function, just for this one. Well, this one I can also sum, right? This is just this sum here. But I can also sum this. This is log, but this bit gives log of 1 minus p, t. This bit gives minus log of 1 minus t. So that's my local zeta function, and I do the exponential of this. I get two contributions, 1 over 1 minus t times 1 minus p to the t. So that's the local zeta function for CP1. Okay, ready? So here is the punchline, which is known as the Weight conjecture. This is power 1, this is power 1, this is 0. These are exactly the Betti numbers of CP1. So this is 1 plus 1 is equal to 2. This is Betti 0, Betti 2, and Betti 0, and Betti 1. So that's the content of the Weight conjecture. It was a conjecture raised by Weight in, in the early part of the 19th century, but it took a long time to settle this. So the upshot is, you take any smooth variety, you count over FPR, do this generating function, it'll always factorize in this way, it'll factorize exactly in this very precise form, such that the powers of factorization of the factors are exactly the Betti numbers of your manifold. And that's very surprising, because somehow, taking product over prime, this is just a choice for any chosen prime, right? Somehow the arithmetic encodes this differential information. That's much more surprising than any of the other 3 ways. And that's why it took all the way until 1974 to settle this one. And this is in general true. So of course, the full one, the Weight conjecture has like 4 parts. About the precise form of this, and so on and so forth. But we only need one simple one. I think Riemann already settled this one. Why the powers of these factors are exactly the Betti numbers of your variety.
What would polynomial of the first Betti number?
What
would it be like? Of course, it's 1. No, Betti of the.
Oh yeah, sorry. So in general, the numerators will capture all of the odd Betti numbers, and the denominator will capture all the even Betti numbers. So this is Betti 0, Betti 2, and if it weren't 1, it would be exactly Betti 1 and all the other stuff.
Yeah, but what the polynomial be?
Oh, something like 1 minus t to like some other factor. Yeah, I can't remember. Actually, I think it's even more complicated. It's like it's a degree, whatever the odd sum of odd numbers, and they will factor out to be something much non-trivial, the roots. So Grothendieck already showed where the roots of the numerators would be. So this is totally surprising. That's totally cool, right? So this is I think every physicist needs to see the Weight conjecture, which is now a theorem. So it's the Weight-Deligne theorem. Why do I emphasize this so much? Because what we're doing now, which Thomas would appreciate, this is the beginning of the Langlands program. Because everything, the other three ways is all geometry, right? You can almost, and combinatorics. So analytic geometry, differential geometry, and combinatorics. Strangely, the fourth piece can be added to it, and it's pure number theory. And the fact that the fourth one should blend into this, that's the beginning of the Langlands program, which is still ongoing, which I still think is it is arguably the most important problem in mathematics, to understand why does arithmetic come into this. Of course, Langlands is one of our 23 challenges. So, but that's just the local zeta function. So the Hasse-Weil zeta function, if you, the global one, you take the product. Right? So you take the product of this sucker, and as you're still doable, you can get factorize it in the Euler product you use twice. You get zeta, Riemann zeta times Riemann zeta minus. So it's kind of nice. So these are almost trivial factors plus some other funky stuff, which I will show you next lecture when we get to the meat of it. So this is every two. Everything I've done is on a sphere. Right? Can you imagine how much more complicated when I move on to higher genus stuff? I stop because the next one is the number 0. So I'll wait for the next lecture for number 0. Thank you.